I am Ashwani Kumar, and I'm from Neuroelectronics Lab in UC San Diego. And I thanks reviewers and organizers to give us the opportunity to present our work in such an August gathering and at such a beautiful venue. I have attended several conferences, but this is one of the venue I really loved it. You have to go nowhere to, enjoy or feel free. So, and I also want to thank you all be here after lunch and you still have some appetite left to digest little more. So I hope you have something on that part as well. So basically I work on energy efficient implementation of MVM operations using filament-free bulk RRAM arrays is a true and prime example of a collaborative work in this field of neuromorphic engineering. And I will be presenting related to our results related to the field. Okay, so I'll present my main results in three segments. First, I will talk about the filament-free bulk RRAM device fabrication, characterization, and then I'll also present a scheme of weight mapping on RRAM crossbar arrays. And after that, I'll present a at edge computing using SNN implementation with our bulk RRAM crossbar arrays. And after that, I will conclude my presentation. So basically, if we look at number of model parameters progression over the years and starting from 2014. So if you look at blue curve, so this blue curve start transition from compute limited era to memory and bandwidth limited era. And this leads us to a memory wall. So basically the memory wall is ever existing in electronic hardware when in the non-human architecture, where we have separate compute and memory units. But because of the implementation and because of the emergence of AI models with billions of parameters, and if we want to implement these large AI models, so this memory wall becomes ever increasing. And this puts us a lot of challenges to implement these large number of AI parameters. And that's why this memory access is a bottleneck for this implementation. And this can be also verified using this figure, where it clearly shows like the multiplication of two numbers, energy consumption of multiplication of two numbers is way order less than the accessing the memory, memory here. So, and usually, well, as a scientist in electronics field, we never look at the implications of these energy figures on environment or on our general life. So basically, this is a very general estimation where it shows like just to have millions of query on Chat GPT, it leads us to 1 gigawatt, power, and which is enough to power entire city for one day, which is equivalent to around 33,000 houses. So what it leads us to put the challenges on hardware. And what challenges are there? Basically, if you want to address those energy values. So because limited capacity, limited on-chip memory capacity, as well as the expensive off-chip memory access leads us to these challenges. So what solutions as a scientific community we can think of? So that is we can stack 3D memories in the backend of the compute unit. So after 3D stacking of this memory, we can also reduce the data movement while performing the compute in memory operations. So I will talk more about this compute in memory operations. So basically how we can define a compute in memory operations. So as we know, like the challenges requirements from AI models, which requires massive training and inference exercises, and they need large amount of memory. And when you need this amount of exercises, you are prone to consume a lot of energy for that. However, the maximum portion of these energy consumptions come from the MAC operations. And we also refer these MAC operations as matrix vector multiplications, which are 70 to 90% contributor for these operations. However, so the key to reduce the overall energy consumption is implementing the energy efficiently, the MVM operation in an energy efficient way. And one of the very prime example to do energy efficient way is the CMOS compatible RRAM crossbar arrays. And I'll explain how we can implement those MVM operations on the crossbar array. So basically, let's say you have an input vector X and you have a weight matrix W and you have another output vector Y, which is coming from the neuron layers, pre-neuron layer and post-neuron layer. So this architecture you can directly transfer on a crossbar architecture, where you can feed your input and you can implement your complete weight matrix on the cross points, which are two terminal memory devices. And your weight values can be translated into the conductances of these memory devices. And this multiplication, the current flowing on the horizontal line is the multiplication operation, and you can sum up those current in a parallel fashion on the vertical lines. So that's how simple it could be. So in this direction, we try to optimize this RRAM technology. However, there is a in literature, there is a filament type of RRAM devices, which is studied extensively. But this device, filamentary RRAM technology, give us four major challenges for on-chip training or on-chip learning operations. First is high forming voltage. So basically, in high forming voltages, you required a very large voltage to initiate the device. Second, it required, you can see the abrupt switching of these RRAM devices. So this abrupt switching creates the noise accuracy loss in your operations. Third, it switches into an extremely low resistance state, which is in kilo ohm resistance. And we know if we have low resistance, it allows the high current flow through it, and it requires more energy consumption. And fourth is the limited number of states. Because of these abrupt switching, it usually shows the binary kind of operations, and it is not good for on-chip learning. However, the solution to could this be, we have bulk RRAM devices, where the solution for these four challenges could be, so this bulk RRAM device provide forming-free operation without forming any filament or without showing you any abrupt switching. So what kind of switching it is? It is area type switching, which provides you uniform switching without any compliance current. You don't have to force any current on the device, and the device will be able to switch. And very important point is the mega ohm resistance. So you can clearly see the difference between kilo ohm to mega ohm. So as soon as you have a device operating range in mega ohm ranges, it automatically reduce your energy consumption. And third is, which is very, very important, fourth is, which is very important again, the multi-level gradual switching, which was not a case in case of filamentary RRAM devices. Here you can have multiple levels and this is very much desirable for on-chip learning. So this is our tri-layer bulk RRAM stack, where we have Al2O3 and oxygen-rich TiO2 and 40 nanometer oxygen-deficient tioxide layer. So basically, the tioxide layer is the main switching stack here, and this main layer in this tri-layer stack, right? So based on that, we developed the crossbar arrays, where we employ the via hole structures, which eliminates the edge effects as well as the high field corners when we use the thick oxide. Here you can see the microscope image of a fabricated 16x16 crossbar arrays, like I show you in a previous slide. And this is the device, which is via hole design. Okay, so basically here I'm presenting the RRAM structure with so in the TAM analysis, which is a metallurgical characterization of the fabricated stack, where the darker region shows of ALD dioxide confirms higher atomic density as compared to 40 nanometer dioxide. And also the line scan profile also shows lower oxygen concentration in 40 nanometer dioxide layer. And here also in the figure C, we can also observe the in nanometer scale dark area pointing to the porous structure of the device. So in terms of switching behavior of the devices, it's because, like I mentioned, we have two layers. One is oxygen deficient layer, which is TiOX, mentioned as in TiOX, and we have oxygen rich layer, which is TiO2. So if we apply a positive voltage, so we were able to modulate the oxygen vacancy distribution in the device by applying a particular field. So if we enable the migration of the oxygen vacancies, so if we able to if we able to migration of the oxygen vacancies from TiOx layer to TiO2 layer, so the effective thickness of the switching layer decreases, which results in a high resistance state. And if we enables the migration of oxygen vacancies from TiO2 layer to the TiOx layer, it enables the low resistance switching, because the effective thickness of the switching layer increases, which is more conductive as compared to TiO2 layer. So this is the switching mechanism for our devices switching into different resistive states. So here I present a DC IV characterization for our devices, or with different diameter size devices. So you can see like the very gradual smooth DC IV characteristic of our devices over different diameter size devices. The next figure shows the resistance versus area plot, where we saw the LRS and HRS switching of different area devices, and it also reflect like it's a bulk type switching, not a filament-free type switching, because it follows the area of the switching resistances follows the area of the device. The CDF plot of the resistance with different devices also shows the low device to device variability in the devices. The next CDF plot for the resistance, it shows the multiple devices data switching between LRS and HRS state, and that's also shows a very high uniformity in the devices. The figure on the bottom right is shows the 50 cycle data from our devices, and the cycles and cycle in the on the 50 cycles also, like all of the curves are like overlapping. So this also shows a very low cycle to cycle variation in our devices. After that, we try to characterize the device to achieve the multi-level states in the devices. For that, we employ two different programming schemes. One is identical pulse programming scheme, where we use the same amplitude pulses to switch the device back and forth in use to achieve the multi-level states. You can see there are many states in the device. To improve this result, we again employ the incremental pulse programming scheme, where we use the pulse amplitude with increasing 20 millivolt. And you can see in this scheme also, we achieve the multi-level switching in the device with better linearity as well as the number of states. Okay, so in terms of crossbar implementation, we also employ a row differential scheme, which is very innovative, and it also helps us to implement the sign weight implementation with voltage sensing scheme for our crossbar arrays. So let me briefly explain this row differential scheme here. So basically for row differential scheme, we choose two RRAM devices which are connecting on consecutive word lines and sharing one vertical lines, this one. So the green device is in a low resistance state and red device is in high resistance state. So we can call it LRS and HRS. So if we apply the positive voltage on the green and negative voltage on the red, it represents the positive weight. If we do vice versa, it represents the negative weights. So this way, with row differential scheme, we can represent the both positive as well as the negative weights. However, the major advantage of this scheme is it increases the effective dynamic range of our devices, which is really help us to enable the mapping of wide range of real valued weights on a crossbar architecture. Finally, this work is in the collaboration with Professor Gutt's lab at UC San Diego, where they built a neuromorphic compute in memory platform, utilizing the switch capacitor voltage sensing scheme, like I presented in the previous slide. So basically, so here I'm showing you the photograph of the board, and we have packaged 16 cross 16 crossbar arrays, which we measured using the voltage sensing scheme, which is more energy efficient as compared to the conventional current sensing scheme. This is a representative read map of a 16 cross 16 crossbar arrays, where we read our 16 cross 16 crossbar arrays using voltage sensing scheme. And at the top right corner, I show you the MVM measured result as well as MVM expected result using the same board, using the voltage sensing scheme. And it's the all measurements points are around the linear line. So this also, so row differential scheme also provide a linearized MVM operation. Okay, finally, in the SNN implementation, so we take a help of, the evolutionary optimization for neuromorphic systems. That is also called Eon's algorithm. You might have listened to a wonderful talk from Professor Katie and on the first day of the conference. So we get the help from those algorithms, and we trained the SNN model using 5 F1 tracks and tested on 15 additional tracks. So this is the representational view of the race tracks obviously on a small scale. And finally, the optimized network. So optimized network look like this, where we have 14 input neurons and 13 output neurons in the network. It's a simplified form of a network. You might have seen in the Professor Katie's presentation, it was kind of messy, so we put it for better understanding in a very organized way. Okay, so after pruning and after getting a final network, which has 14 input and 30 output neurons, so we try to implement then we extracted the old synaptic weights from that network, and we implemented on our 16 crossbar arrays. And to employ that, so we use 2 crossbar arrays because we need to implement in a differential way. So this is the weight map which we needed. This is the ideal requirement. And this is the weight map which we programmed on to our crossbar arrays. So basically, if you see on the Y side vertically, you have 28 lines, because we have differentially programmed the lines. Although we have 14 nodes, but because we are programming differentially, so we need 28 lines. So that's how we programmed this one. And the result for this, you might not be seeing the difference because there is not a much difference here. So because this is ideal software computation, this is using the hardware-based synaptic programs, programmed weight. So they are pretty much matching with each other. However, here you can see a little bit difference here. So we have different speed numbers, which is the output of the networks, and the angle values as well. So, and these are the speed numbers where you see number of time it uses in a network, and you see it is basically very much matching with the ideal software performance. After that, we thought of to benchmark our bulk RRAM technology with already existing very popular filament-free device technology. So basically for that, we choose CA-Leti filament-free device. Then next, from UCSB, Professor Strukov's group filament-free device, and one of the device we choose is from T-Singwa group here. So basically you see, like, when we implement the same network, same weights using our scheme, our bulk RRAM crossbar arrays, it reduces the overall energy consumption by the order of 2. Conclusion. So finally, we developed a novel tri-layer filament free bulk RRAM crossbar technology. We proposed a row differential weight mapping scheme to achieve higher dynamic range for mapping a wide range of real valued weights in bulk RRAM crossbar arrays, performed highly linearized MVM operations in an energy efficient way using in-house designed neuromorphic compute in memory hardware platform. We also presented SNN implementation using our bulk RRAM crossbar arrays for autonomous tasks for scale F1 tracks, and shows a great agreement with ideal and software results. I also want to mention, like, our bulk RRAM crossbar arrays for edge computing applications substantially reduce the energy consumption compared to other filament-free technologies. And the developed technology has a capability of multi-level switching in mega-ohm range, which is very energy efficient, as well as it is CMOS backend of line compatible. So we can also do 3D stacking, like I mentioned in my introductory slide. The acknowledgement, without this work would not be complete. So basically, I want to really thank collaborators, Professor Gert's lab, Professor Catherine Schumann's lab, as well as Professor Ivan Schuller's lab, and my group members. And this is our neuroelectronics lab group, and we have funding agencies which really supports our group, like you see on the slide. And thank you. And with thank you, I also want to mention one more point here. So basically, this work today accepted or published online as a Nature communication paper. and you can also go there, you can look there, and it is a sheer coincidence, like my talk and the work coincidences together. So, and with that, I also want to say, sometime I think like we live in a simulated world with so many hardware, so we don't know. Thank you so much.